The new section is entitled Angles Related to Circles. There are a number of theorems and definitions in this section. Let's go over some definitions. Inscribed angle. Basically, if you pick a point on the circle and you draw two chords from that point on the circle, you just designed an inscribed angle. If you take one point on the circle and through that point or from that point you draw two chords. Remember, a chord goes from one point on a circle to another point on a circle. One point on a circle to another point on a circle. That is an inscribed angle. Now, we are going to draw a tangent chord angle. Tangent chord angle. Oh, sounds like we're going to have a tangent line and a chord. So through this point, and we're going to end up with an angle. Through that point that I just highlighted, I draw a tangent line. And then through that point, I draw a chord. Goes from this point of the circle to any other point of a circle. This here is a tangent chord angle. Again, you have any tangent line, and then from the point of tangency, you draw a chord. That is a tangent chord angle. Okay, the way they named them, or named this, was pretty good. You might want to call an inscribed angle a chord angle. One chord or second chord. Chord angle. But we also call that inscribed. Now, we're going to look at our theorem. Remember, if you have a central angle, whatever this angle is, call it theta degrees. This arc was also theta degrees. But what if it's not a central angle? What if you have an inscribed angle? It turns out that if this is theta degrees, then the arc would be twice it. If you have the arc and you want this angle down here, take half of the arc. And that's what this theorem states. So let's write up this theorem formally, and we'll even prove this theorem. Okay. The measure of an inscribed angle or even our tangent chord angle, I suspect, even a tangent chord angle is going to be 1/2 the measure of its intercepted arc. Is 1/2 the measure of its intercepted arc. For example, if this is an inscribed angle, this inscribed angle intercepts that arc. And if this arc is 70 degrees, then the inscribed angle will be half of it. Same thing if you have a tangent chord. Tangent line and a chord. This angle intercepts this big arc. If this big arc is 210 degrees, then this angle is half of 210. It's 105. How would we prove such a theorem? Well, there's going to be a number of cases. They all involve the center. Suppose the center is in between the inscribed angles. In other words, in this inscribed angle, the center is outside. And of course, the third scenario will be that it's not inside, the center is not inside or outside, but it's actually on one of their legs. Okay, so those are the three cases we are going to have to consider. Now, let's see the best way of doing this. Let's call this A, B, and C, and center O. Now, what do we know? Well, let us draw the following. Let us draw the following line, and let's call that point B. So basically, I want to show that angle B is 1/2 the measure of arc CA or CDA. Actually, it's probably best to do one of the other three first. All right, let's do one of the other three first. In fact, let us do the one where the center is right on one of their legs. And we will call it A, B, the vertices C. Okay. So again, I want to show that the measure of angle A is 1/2 the measure of the intercepted arc. Well, the arc is BC. That is what my goal is. Now, let me go like this. Let me go like that. Now, the measure of angle BOC, the measure of angle BOC. Now, this is a central angle. So this angle is actually equal to the arc. This is equal to the measure of arc BC. But it turns out that angle BOC is equal to the angle BOC is equal to angle BAC plus the angle ABO plus the measure of angle ABO. What I'm saying is angle BAC, this angle here, plus angle ABO, this angle here, is equal to the complement of the angle where I put the question mark by. And the reason is, what properties does that angle have? Well, when you add that angle, you get 180. And what other property does this angle have? Well, when you add these two angles, the sum of those two angles, you also get 180. That is why these two angles here is equal to the exterior of the third angle. Okay, so I have two ways of writing that. This way and this way. And these two are equal. The measure of arc BC is equal to the measure of angle BAC plus the measure, I really should be writing the M, plus the measure of angle ABO. But what do we know about these two angles? Well, if you look at the triangle, look at the picture carefully, and you ignore OC for a moment, you say, oh, AO and BO are radii of the center. That is, we have an isosceles, and they're equal. So we have an isosceles triangle. So these two angles are equal. These two angles are equal. So what I can say is, measure of ABO is the measure of BAC. The measure of BC is equal to 2 times the measure of angle BAC. But BAC is just angle A. It's 2 times the measure of angle A. And if this equals this, if I divide both sides by 2, I get exactly what I wanted. The measure of the inscribed angle is 1/2 the measure of its intercepted arc. This arc right here. It really was true. Okay. So now that we have that ammunition, now we can do the other proof. Let's go back. Yeah, let's use a whole clean page. Now with that ammunition, we can do the next proof. But just to remind you, so what we proved so far is, if you have an inscribed angle and one leg is a diameter, that is, it crosses the center. Okay, you have an inscribed angle where one leg is a diameter. Well, we just proved that this arc is twice that angle. We already know from our previous proof that the measure of angle A is 1/2 the measure of its intercepted arc. So we know this now, okay? And we are going to use it pretty heavily. Okay, so now let us do the next proof, or the next case. What if the center is inside? So we still have A, and we have B, and we have C. Well, it works so nicely when we had a diameter. Let's use the diameter bit. Let's call this D. Okay. To make things a bit easier, let's call that part of angle 1A, part of angle A1, and the other part 2. That is, angle 1 plus angle 2 is angle A. Now, let us just talk about that picture, the one without angle 2. Well, using the theorem above, we know that the measure of angle 1 is equal to 1/2 the measure of the arc BD, the measure of its intercepted arc. Okay, I'll play the same game with angle 2. That is, ignore one of those lines. Ignore that line. We know that the measure of angle 2 is 1/2 the measure of the intercepted arc, which is DC. This arc right here. Okay, let's put this back, and now we do something called arithmetic, where you're going to add. When you add the measure of angle 1 and the measure of angle 2, you get the measure of angle A. And on the right side, I can factor out a half. When I add, I get half of the measure of arc BD plus the measure of arc DC. So the measure of angle A is equal to 1/2 of what's inside. But the measure of BD plus the measure of DC, that's the measure of BC. The measure of arc BC. BC is the intercepted arc of A. This is angle A. Here's angle A. This is the intercepted arc. And I just showed that the measure of angle A is half the measure of the intercepted arc. Okay. This was a case where the center lies in between that inscribed angle. What if the center is outside the angle? Why do I picture a subtraction coming up? So we have a circle, and here's the center, and our inscribed angle is like that. This is O, this is A, this is B, this is C. And I would just love to show that the measure of angle A is 1/2 the arc that it cuts off, equal to, oops, I already have the half, is equal to 1/2 the measure of an arc BC. And like before, the theorem that we proved, the first case that we proved, we're going to use that fact. Let's go like this. Call that point B. Okay, so now, temporarily, let's ignore that line. So that initial theorem we had, okay, so but there is one little problem. Angle A is this angle. That's angle A. Let's call it 1. And let's call this angle 2. So the whole thing is 1 plus 2. Just remember that angle A is just angle 1. Okay, and let us ignore this. So this big angle, the measure of angle, the measure of angle 1 plus the measure of angle 2, this big angle here is 1/2. Now, since the center is on one of the lines, one of the chords that made up the angle, we can use that initial theorem. This is equal to 1/2 the measure of the arc that angle 1 plus 2 cut off, which is BD. BD. Okay. But we did too much. We never had this angle 2. What is this angle 2 all about? Well, the measure of angle 2 is equal to, now what we can do is ignore that portion of the diagram. Angle 2. Well, the center is on one of the chords. So the measure of angle 2 is equal to 1/2 the measure of its intercepted arc, which is CD. Okay. Now, the reason I want to subtract is because I want the measure of angle A, and remember, that's the same as the measure of angle 1. On the left side of the equal sign, when you subtract, the measure of angle 2 disappears. So you just have the measure of angle 1. And on the right side, I can factor out the half. You have 1/2 the measure of BD, arc BD, minus the measure of arc CD. Okay, well, BD is right here. Measure of arc BD. Well, if I take away the measure of CD, if I just take away CD, what I'm left with is the measure of arc BC. So the measure of angle 1, which is A, is 1/2 the measure of the arc BC. Okay, now let's get rid of the line that we put in, and now we have exactly what we want. The measure of angle A, is 1/2 of this arc, B to C. It's 1/2 the measure of arc BC. So we proved it. We had to do 3 different cases, and the first case helped us do the remaining 2 cases. So now we know, not because I told you or your teacher told you, but because we proved it. We know that the measure of an inscribed angle is equal to half of the arc. Okay. If you have, so some definitions. If you have 2 chords, that angle right there is a chord angle. Of course, so is this angle here, and this angle, and that angle. Depends upon which one you want to talk about. Okay. Now, it'll be nice if we knew something about the chord. Okay, so let us just concentrate on that initial angle I put. And it'll be nice if we knew the relationship between the chords that were cut off. we have this chord, we have that chord, and we have a third chord and a fourth chord. Okay, well, it turns out that the angle in question, so let's label this A, B, arc A, arc B, arc C, and arc D. And we'll call this angle X. Turns out that angle X is the average, the measure of arc A plus the measure of arc C over 2. It's the average of the chords. And remember, this is also angle X. So it's the chords, the average of the chords that angle X cut off. Angle X cut off this arc, and the other angle X cut off that arc. Okay, the average of those two arcs will equal angle X. In other words, if this arc was 70 degrees and this arc was 30 degrees, the measure of X would be 70 plus 30, 100, over 2. It would be 50 degrees. It would be 50 degrees. Angle X would be 50 degrees. Now, let's state the theorem and let's prove it. Theorem. I think it'll be nice to have a diagram. A, B, C, D, X. So, chord theorem. Angle X is equal to, so there are two angle X's, and this is what they cut off. This is what they cut off. Angle X is equal to the measure of the arc AB, plus the measure of arc CD. The measure of arc AB plus the measure of the arc CD. Half of that. Okay. How would we go about proving such a theorem? Okay. So, what's bothering me? Okay. So, how about, this is a ticket. How about we do such? Make a triangle. Well, this angle 1 plus this angle 2, not this angle, but it must add up to the complement. That's the word I meant to use earlier. Supplement. Okay? You have a theorem, and we talked about this theorem. If this is angle 1 and this is angle 2, well, this angle is 1 plus 2. And the reason is what do you add to 1 plus 2 to get 180? Let's just say, for argument's sake, 3. Well, remember, these two angles inside the triangle add up to 1, 2, and that third angle is what you must add to 1 plus 2 to get 180, which is 3. So yeah, that is 1 plus 2. Okay. The only thing is, I just would like this picture to be a little bit bigger. Angle X, A, B, C, D, and then we decide to draw this line, 1 and 2. And 1 plus 2 equals X. Angle 1 plus 2 must equal the supplement of that third angle. The third angle being this angle, and that's the supplement. Okay, so we know that the measure of angle X is equal to the measure of angle 1, like I've been saying, plus the measure of angle 2. But now, what is the measure of angle 1? What is the measure of angle 1? Okay, angle 1 cut off this arc. So it must be 1/2 the measure of arc CD. And what is angle 2? Well, angle 2 is this angle, and it cut off that arc. And it's angle 1 as well as angle 2 is an inscribed angle. So it equals to 1/2 the measure of the arc that it intercepts, AB. But this is where I have you. I can factor out the half, and I get the measure of arc CD plus the measure of the arc AB. And we have a rule saying instead of multiplying by a half, you can divide by 2. And we have another rule saying when it comes to addition, you have the commutative property. You can switch the order. And now it looks just like what this theorem started with. It's exactly what we wanted. So it really is true. It really is true. It's not because somebody told you it's true. One of the problems I think in studying math is students accept too many things and then they're just overwhelmed. It's like, what can I use? You can only use things that you can prove, in my opinion. Okay. Now, all the angles we've drawn so far were interior. Let's draw exterior angles. You have a point outside, and you design an angle that way. This is called a secant to secant angle. You have a point outside the circle, you go tangent, and you go secant. This angle here is called a secant tangent angle. They define them, or they name them very nicely. You have a point outside, you go tangent, you go tangent. This angle, tangent, tangent angle. Tangent, tangent angle. Okay, now let us talk about the measure of that angle. What's the relationship between the angle and the arcs? And it doesn't matter whether we're secant, secant, tangent, secant, tangent, tangent. AB, arc CD. Arc AB, arc CD. This is P. The measure of angle P is half the difference of their two arcs. Angle P, it has these two arcs. It's going to be, now when you subtract, you always do larger minus smaller. It's the measure of arc AB minus the measure of arc CD all over 2. All over 2. And if you have a tangent secant, this is P. You have this arc cut off, AB, and you also have that arc cut off, AC. Theorem is exactly the same. The measure of angle P is the big arc minus the little arc over 2. If you have tangent, tangent, A, B. So now, I want to say it's this arc, AB, minus this arc, AB. Well, that's not very clear. So I put another couple of points. So angle P is equal to the measure of AXB, this big one, minus the measure of arc AYB, minus the measure of arc AYB, AYB, all over 2. It's the big arc minus the small arc over 2. That's to get the angle, the measure of the angle that is outside. That one I'm going to leave, well, I'll prove the first one, secant, secant. A, B, C, D, angle P. Okay. So now you have our center. Let us modify the diagram by doing such a thing here. Call this out an angle 2 and angle 3. And what we know is, consider this big triangle here. Like always, angle 3 is equal to angle 2, angle P, plus angle 2. Because this angle equals both. Sorry. Call this angle 1. You know that angle 1 plus angle 2 plus angle P is 180. And you know that angle 1 plus angle 3 is 180. And you subtract. The angle 1's cancel out. You have angle 2 plus angle P minus angle 3 is equal to 0. Well, this must equal that. That's why the difference is 0. Okay, that's exactly what I stated here. So, angle P is angle 3 minus angle 2. But what is angle 3? What is angle 2? Well, angle 3 is an interior angle. It equals half of that arc. It equals half of that intercepted arc. So angle P is equal to angle 3, which is 1/2 the measure of AB. Minus angle 2. But angle 2 is interior. Angle 2 cuts off CD, arc CD. So angle 2 is 1/2 the measure of CD. But this is it. Factoring out the half, you have the measure of AB, arc AB, minus the measure of arc CD with a half in front. But instead of multiplying this whole right side by a half, you may divide by 2. And that's exactly what this theorem stated. And why did I put angle 3 and angle 2 where I did? By the way, I was thinking that's like angle 1. The reason is because I wanted these intercepted arcs. That is why I drew this line. That's why I drew that line. Because angle 3 gave me this arc, and angle 2 gave me that arc. I want to show that they're half the difference with angle P. Okay, so I did that. That's another ammunition that you have. In this section, it's going to require a lot of studying because there's a number of theorems going on. You have inscribed angles, you have exterior angles, tangent, not tangent. Okay, so now we can actually attempt to do some problems. Suppose you have a picture like this, and they tell you 50 degrees and 80 degrees, and they say find angle X. Find angle X. Well, angle X is equal to the average of the arcs it intercepts. Remember, that's also angle X here. This angle and this angle. Angle X is the average. It's 50 plus 80 over 2. It is 65. That's angle X. Suppose we have a similar diagram and you're told this is 50 and maybe this is 80 and you're asked to find arc Y. Now, when I say 50 degrees up here, I mean that arc. And 80 degrees, I think that one's obvious. When I talk about Y degrees, I mean this. Well, just like the last problem, you add up the arcs, opposite arcs, and you divide by 2, and you get the angle, 80 degrees. So this must be 160, because only 160 divided by 2 is 80. 2 times 80, 160, is equal to the top. Well, what do you add to 50 to get 160? And whatever, we're calling that unknown Y. Well, if you add 10 to 50, you get 60. And you add another 100, you get 160. And that is the answer, 110 degrees. Suppose we have this problem. 150 degrees, 30 degrees. Find X. X being this arc. Well, 150 minus X, when you divide it by 2. When you subtract these two arcs and you divide them by 2, you get that angle out there, 30. 2 times 30 degrees is 60 degrees. And that must equal the top. 150 minus X is 60. Well, you really should know that if you take away 90, you'll get 160. 150 minus 90 is 60. So it turns out that that arc is 90 degrees. Don't really get caught up with tangents and secants. If the point P is outside, you subtract the two arcs. Divide it by 2, and you get the angle outside. If this is 40 degrees and this is 110, this being that amount, how much is X? How much is that arc? Well, 110 minus X, when you divide it by 2, it gives you that angle outside, 40. 2 times 40 is 80. And that product equals the numerator. 110 minus some unknown number is 80. You should really know that 110 minus 80 is 110 minus 30 is 80. That must be 30. 110 minus 30 is 80. 11 minus 3 is 8. But we keep getting these zeros. So X is 3 with their 0. Here's a very straightforward one. If you were told that that arc is 80 degrees, what's that angle? And the answer is, it is half. Let me tell you how I remember it's always half. I mean, we proved it, but here's an argument that I'll give. All the way around is 360 degrees. You can always make a triangle. This angle cuts off that arc. This angle here cuts off that arc. And this angle here, it cut off this arc. Well, the arcs is 360 degrees. And the angles, the sum of the arcs is 360. The sum of the angles is 180. The arcs is twice the angle. The angles is half the arcs. I remember that. So if this is 30, I have to double it. If this is 80, I have to double it. If this is 140, I have to half the angle. That's how I remember it. But that's not a proof. That's not a proof, but it helps you remember it. At least it does for me. Here's a nice problem. You have an inscribed triangle. It's given to be isosceles. And this arc is 140 degrees. Instructions are, say, to find the angles inside. Find the three angles inside. Find everything. What does everything mean? Find out this arc, find out the measure of this arc, and the three angles inside. Well, we're given one arc, and what you need to do is look at the arc that's given and decide what angle cut off that arc. And the answer is this angle cut off that arc. And it's an inscribed angle. So it's half the arc. If the arc is 140 degrees, then this is 70 degrees. And then you say, oh, this must also be 70 degrees. Why is that? Base angles of an isosceles triangle are equal. The sides, the angles opposite the equal sides must be equal. And then you say, oh, this angle 70 degrees, this 70 degree angle cut off that arc. It must be 140. Now you have two ways to proceed. You can say, so far, the arcs added up to 280, and there's only one arc left over. Well, if you add 80 to that, you get 360. So this arc is 80, and this angle, remember, this angle right here, cut off that arc. So it's half as much. Or, like I said, there was another way. In that triangle, you had 70 and 70, that's 140. You add another 40, you get to the 180 that you need. Hence, this angle is 40, and the arc opposite it must be twice 40, or 80. That's a nice problem. How about this one? You have this, you have this, you have that. We did not necessarily cross the center, and these two lines are given to be parallel. And you're given that this arc is 40 degrees. And I will change my mind about something. Sorry. It does cross the center. Solve for the circle. That is, find all the arcs, find all the angles. Well, no, I have 40 degrees arc. I look for the angle that cut it off. It's that angle. So this angle is half for 40. But the two lines are parallel. And here's my Z. This angle is the same. It's also 20 degrees. Oh, but that new angle cut off this arc. This angle cut off the arc that I just highlighted. It's an inscribed angle. Double the angle. You'll get the arc. Okay. Now, if you have a diameter, I can tell you what that arc is. It's half, 180 degrees. Well, let's label it differently. This arc is the other 180 degrees. This is a diameter. It did cross the center. That was given. That means this arc is 180. Oh, if this portion is 40, then the other portion, the remaining portion, must be also 140. Same thing. If this is the diameter, down here, this halfway around, it must be 180. Well, if this portion is 40, then the rest is 140. And unless I'm missing something, I found all the angles and I found all the related arcs. This 140 is only that portion. You had to cross the center in this case to find the 140. Here's a problem that we should be able to do. I am not going to say that these two lines are parallel. I am not going to say that. But I'm going to say that this is a 40-degree angle, and I want us to find angle Z. I want us to find angle Z. Circles, inscribed angles, chords. This 40-degree angle cut off this arc. Angle Z. Angle Z. Cut off the same arc. This is also if two inscribed angles cut off the same arc, they must be equal. Okay, I mean, why is that? Well, since this is 40 degrees and it's inscribed, the angle that the arc that it cut off must be double. An angle Z cut off an 80-degree arc, so its angle should be half of 80, which is 40. So this is pretty neat, what I'm saying. Let's consider this arc here. What I'm saying is this angle and that angle and this angle, they're all the same. They all cut off this arc. This angle, they're all the same. If two angles cut off, if in a given triangle, if in one given circle or two congruent circles, if two angles, inscribed angles, cut off the same arc, those angles are equal. Because if this is angle X, then the arc is 2x. And if the arc is 2x, then that angle must be half of it. If this angle cut off an arc of 2x, then this angle must be x. If this red angle cut off an arc of 2x and it's inscribed, then the angle must be x, must be half of 2x. These angles are really all equal. Okay, on that note, this finishes the sections on angles related to circles. Very important stuff.